Hi, and welcome to this week's Programming Quantum Computers. I'm Lynn Langit. We've got a good group this week, and this week Matt has kindly volunteered to lead our discussion of the next chapter, and we are on chapter 11. Is that right?
Yes.
So we are getting there. There are 13 actual chapters. There's 14, but 13 chapters with substance in them. So with that, I'm going to turn it over to Matt, and we'll kick it off.
Thank you. So Jeremy, if you can share your screen there.
Sure.
I'll annotate over it as necessary. I'll also probably jump over. I think there's one code thing I might show. Some of the code in this chapter is pretty lengthy, and unfortunately the website does not display the circles as nicely as the book does. So it's almost easier just to continue to use the book, but definitely jump in here. So anyway, so yeah, this is all on quantum super sampling. And so he's talking about what can you do for computer graphics. If you're not sure what super sampling is, computers use it all the time, definitely in video games and rendering, but it's pretty much anywhere you have graphics and you have anti-aliasing going on. So what that is if you've got an image with hard edges and they don't fit nicely into your pixels on your screen, that can cause a lot of distortion and a lot of mess. So what they do is they actually sample a much higher resolution image, and then they'll take those various pixels or shots, and they show some pictures about this later as well as how they do it, but they reduce that into a smaller image that conveniently fits on your screen. So for rendering or a video game example, your screen may be HD, but you're sampling this huge environment and world, and there's all these calculations and things going on. And so to make it not look jittery like in the old days with 3D technology, to actually render or partially render a much larger resolution image, and then they sample it down to the size of your screen so it looks very smooth. And so that's what he's talking about here. So yeah, so he shows some examples. We've got some nice grayscale type images there on the left, the ideal sampling reference. And he mentions there's different ways they can sample these, but Monte Carlo on conventional computers is pretty general. And so that's just basically a random shot as far as how they sample. They'll look at, I think in here, I don't know if he mentions what grid size they're using, but a lot of times you might sample a 4x4 grid, so 16 pixels, and you'll sample that at high res to come up with 1 pixel that you're actually going to show on the screen. And so when you decide, well, if I've got these shades of gray, which pixel am I using? And you can't just pick the one right in the middle, but that doesn't offer great results. And so Monte Carlo is one of those methods they'll randomly pick a pixel to look at. And then quantum super sampling does it a different way. And one thing I like he mentions is QSS, quantum super sampling, originally developed as a way to speed up super sampling, and by that it failed. So here's a great case. Well, we thought quantum was going to be a great leap forward, and it actually was not. But one thing you did say is they came up with some interesting results that are worth looking into. And so he shows the things here, and he says the mean pixel error is 2%. And so what I think that means is out of all the pixels, how far was that pixel off? If it should have been a really nice gray, was a little too white, a little too dark. So 2%, that doesn't sound too bad. Error-free pixels are 34%, so roughly a third of the image is perfect. On the quantum side, you actually have a slightly less error, which is nice. And 41%, nearly, 20%, out of every 5, or almost close to 1/2 of all the pixels are actually perfect. So that's interesting. You can see the pictures are a little different too. Rather than this weird noisy shades of gray, you've got almost little dots or flecks and stuff in there. And so I think I need to take control here before I can click on your screen.
I mean, imagine what this can do for medical imaging. I don't know that time is your factor.
Yeah, I don't know. I think there's a lot of different things that would be fun to explore. And later on, he talks about it. But this is one of those things where a lot of the standardized work would still be on a conventional computer, and then you would throw the sampling side of things off at the QPU. Right now, they're doing some pretty amazing things in medical imaging where they're actually using GPUs and graphics accelerators to take the rendering time of MRIs and some high-end brain scans from several hours down to a number of minutes. So I think the world is getting used to instant medical results. I wonder if throwing these at a cloud GPU is going to render the same desire. It'll be interesting. So anyway, so he says, yeah, in the quantum image that we saw before, some of the pixels are very noisy. You have black and white specks while the rest are perfect. So he gives the example that says, say you were, okay, now clear out those noise. Now with the result, clear out the noise, make it nicer. It's a lot harder to do in the noisy granular picture than it is in the quantum picture. That's a little bit of a contrived example, but I suppose it could happen. It depends on what you're trying to do. But I think his main takeaway there was it offers some interesting differences that we don't normally see. Then he gets back into talking about what super sampling is like. So again, we've got this large scene, we've got this array of pixels, and you're picking one pixel. And so what they typically do is they'll cut up the scene into a set of squares or grids. And he calls those subpixels. And so you'll actually, not the grids, but there are subpixels within the grid. And you'll sample one or more of those to come up with what your single pixel should be. I did look up in Wikipedia just about super sampling, and it was a pretty easy article, nice to read. And they actually go over several different methods that are used to try and pick up, whatever that main pixel is. So that's kind of interesting reading if you're interested. And I'm just kind of going through this, so definitely chime in if you have anything else to add or something that caught your attention. I did have to read through this chapter twice. I'm still not quite sure I got absolutely everything. Actually, I'm sure I didn't. But he starts introducing, okay, now let's create images. And I was kind of lost. I'm like, we're not sampling anything. We're just using fancy math and code to create cute images. And then I realized, oh, I missed a couple of important sentences here. So right off the bat, he says, to make use of the QPU for super sampling, we first need a way of representing images in the register. And so kind of going back to previous chapters when we're looking at how do we start applying, we need some way to get our data into the QPU so that we can start working on it. And he's shown us a couple of different ways to do it. Reading from RAM if we were to do that, or using formulas to set up our data. So we're kind of in the same way here. We're not really importing an image, but we're using fun code techniques to create fancy graphics that will later on actually use QSS on. So in this, he brings up the idea of a Qpu Pixel Shader. And again, you can look that one up. I had to because he was referring to it a little differently than what I was used to. But all a pixel shader is like a function. It's a set of code that alters that pixel in a specific way. And so it could be used to add fog, add a glow, add all kinds of things, add blur or acceleration blur or movement blur to an image, things like that. In our case, we're getting really basic. He's starting off with a blank canvas, and his pixel shader is literally just going to draw or flip the phase on pixels that he wants to flip it on. So we're not analyzing anything. We're not taking an initial image and the pixel shader is analyzing and filtering it or altering it in some way. He's using the pixel shader on a blank canvas to literally start to draw his patterns and what he wants. And so we're actually going to flip phases, and this is the way we're representing things. So we're going to flip the phases and then use our amplitude. Oh shoot, I just lost it. AA.
Amplitude amplification.
Yeah. to sort of, change the way those look and represent them. So what he's going to do here, we've got 2 registers that two 4-qubit registers. So we've got X and Y, and of course it comes out as grid. Try as I might, I ran this code, I increased my screen, I decreased it, I did everything. I could never get a layout that looked like this. It was just completely all over the place. So I will, again, just stick with the book on some of these examples. But he starts with this blank canvas. And then he basically says if Qx is greater than or equal to 8, then we're going to invert the phase here. And then we get this nice screen over here. And then later on, he says, okay, and this is where I got a little fuzzy. I was trying to follow the logic and I kept getting a little lost. I don't know if I was just getting a little too much in my head. But again, he's using some logic, and then we're going to flip it again. If X is greater than 8, and we're doing a Q naught with X and Y. And it kind of came out to be if both the lowest bit of Qx and Y were the same, then we're actually going to leave it flipped. So right here, they're both 0, green. All the way down here, they're both, the lowest bit is both 1 or green, and that gives us this checkerboard pattern. That's about as in-depth as my understanding of his code here went, and I don't know, I was having a mental block. Did anyone else want to add to what he's actually doing here?
I would just say that this is a very contrived example. He said that, but the thing that it probably makes it a little bit difficult to grok is he is drawing with quantum operations, but that's not really what you do in the real world. He's doing that to make what is going on visible. It's kind of clever in an interesting way, but it's not, it's contrived. And so that's, you're feeling like this is kind of strange, and it is a bit. So just kind of go with it. This is really just so that you can see what a representation of data would look like. But this is not like what you would actually do for a shader. Do you know what I mean?
Yeah, and I think you made a couple of really good points there. One is this assumes we need some way to visualize how an image would be stored. Mm-hmm. And you don't normally see a memory register and go, oh, that's an image, in normal classical. So he has come up with a way for it to make it a little easier. If we were to see, a register of a 1-bit image, where it's either 0 or 1, we could do something similar. Also, like you said, it's kind of contrived. If you do any real minor hello world type graphical programs, whether it's in JavaScript in your browser or something else, you do start off with these simple examples. You tend to have higher order operations like draw a circle with a radius. But to do anything beyond that, you do start to get to some of these, contrived. Draw a line 10 pixels long, turn right. If you remember the old logo days, turtle, draw another 10 pixels, turn right, and then you loop through that 4 times. Oh, I made a square. Couldn't I just use the square operation? Sure, but we're teaching you looping and steps and everything else. But so again, we're not super sampling here. We're just coming up with some fancy, fun ways to kind of get what we would call an image into our system. We never actually use this one. In fact, in many of the ones he doesn't use. So he has some other code to create some other graphics. Again, this looks great in the book. I did not get this to render very well on my screen. I do want to, Neri, I have these grand ideas in my head to play with the code that actually renders circles.
Did you see the Easter egg on there? That in some of those examples, it actually outputs a PNG or a GIF or something. It actually outputs a graphic.
It does, and I'm ready to show my screen when we get to some of that. And I was pretty impressed, and then I realized, oh, you're using JavaScript canvases and HTML canvases to do that. So obviously it has nothing to do with quantum, but he did some clever stuff, and it I don't remember seeing any of that in the cheat sheet. Maybe it's there, but kind of shows that.
I think another one of the problems is, I think for the drawing curve example, there, in addition to the QY and QX registers, there's also a QAC, another accumulator register. So I think that even if you could get all of the circles to display on the QC engine page, it wouldn't be the right circles because it would include the accumulator as well as the QX and QY.
Yeah, and that was some of the difficulty. So some of my grand designs, I almost want to say, okay, is there a way we could add parameters? Just show me the circles within these coordinates or metrics or key points. So again, he's just showing some ways to get in there. I liked how he did say, where was it? Yeah, in this case, the math must be performed in a larger 10-bit qubit register to prevent overflow when we square. So again, that gets into our overflow idea, but then he does go on to say later on, I don't remember if it's the next page. Yeah, if it's too small, the math performed will overflow, resulting in curved bands. This overflow effect will be deliberately used later on the chapter. So that only made me laugh because again, you know, you're talking about old DOS, you know, gaming days. There were a lot of hacks and tricks that developers would work around what the hardware could do. And what makes that even more fun is if you've ever played retro games or used emulators, they've had to purposely break emulators because when the emulators were working correctly, none of the hacks worked. So you'd have games that would break because it was assuming I'm only using 8 bits of memory and I know I'm overflowing. Well, hey, you know, we're on a 32-bit, 64-bit PC. We'll give you all the memory you want. No. I was planning on only having 8. And so they've had to actually build these restrictions to some of the emulators. But anyway, that was just a fun throwback. I enjoyed his comment there. So now we can represent images in the phases of quantum registers. Let's return to the problem of super sampling. So again, we have many pieces of information. He's saying we're going to, and yeah, he does have a weird text error here. So want to combine to give a single pixel as our final output image. Software verification is not there. That's not supposed to be there. To simulate this, we consider using a 16 by 16 array of quantum states made of 16 4x4 tiles. And so this gets back to, imagine this is the entire image. We're only going to work on one tile of this image at a time. And then again, this is very common because your high-res image or whatever you're sampling, whether your ray tracing is often much larger than your conventional memory can allow. And so you'll work on a snippet of this at a time. Now, his example here, before when we were using fun qubit operations to draw images, he's actually built in to his qubit operation what grid he's working on. So he's not like saying, I've got this image, let me just slice off a portion of it and working on it. He's literally going to draw just that portion of the image into the register. He picked, let's see, as his default. Well, he picked where X is 2 and Y is 3. And if you run it, you actually get this image here. And so I played around with it and I said, well, what if Y is 0? Because that's a much more interesting sample. And that was that grid right there. Did any of you guys run this at all? I ran it and I've got it on my screen. Just happy to show it.
Yeah, I'd like to see that because
Yeah.
I was having difficulties getting useful visual outputs.
Yeah, so I'm going to share my screen. Oh, I can't share my screen while you're sharing. Okay, of course, my screen's going to bounce around the whole time while I do this. So I know you can't see anything right now. Okay, you should be able to see this, correct?
Mhm.
Yes.
Okay. So here he's got his, X equals 2, Y equals 3. And again, it's not showing up very well. And if we run it, this is what we get. And now, you know what? I don't know if I can do this. Yeah, I can select. See what happens if I do this. Oh, that did not let me select them. I can share my whole screen, but it's quite large. I'm afraid you might not see it. Let's do this. Okay, I know you can't see that right now. 1 second here. Perfect. Okay, can you see part of my screen?
Yes.
Yes,
Perfect.
drawing canvas.
So I just grabbed this portion of his screen right here, and this is what it comes out. Now remember, this isn't stacked correctly, but if we were literally take these guys and move them over, this is the XY that he found, that he did. Again, we're going to ignore the rest of them. So if we say, well, let's do the more interesting one, let's see where Y was 0. That's where they actually cross. I'm gonna hit run. You can see our dots changed a little bit here. I'm gonna grab that.
There's a little resizing handle on the UI box. It's 2 diagonal lines at the bottom corner.
Yes, I never got that to work well for me.
Yeah, it only goes so far, and then it crops the circles.
Yeah, and even when I tried to do this, ideally they would stack up on each other 4x4. I can get them to stack up like that, but then it doesn't actually expand. So this is, and it may be a Chrome thing, not sure, Firefox or any other browsers, which is better. But going back to what we had, if I grab this and I go and I stack that on top, sure enough, now we see that grid that we had. So he is literally.
That's cool. That's really helpful.
Yeah. See, I never would have thought to do that. So
Yeah,
that is
that's really
very
good.
helpful.
Yeah.
And these small grids are the only time it works. As we get into those 64x64, all bets are off. So Nuri, if I ever get time, which what developer has time, I'd love to dive into his rendering code. And if the developers are listening, we've got some fun, issues to put on your GitHub there. So that's what he's doing here. Again, though, in my mind, he's not taking an image or data as you would think of it. I've got data. Let me just grab a small portion of that. He is actually changing his drawing code so that he's only drawing the portion that he wants. Again, that's a little different than what you normally see in graphics. But any other comments on this particular example before I move on? Okay. So, but he's basically showing, okay, let's put some parameters in here and target on one small section of the grid. So now we have a more interesting image, and this is the one we'll actually be working with to super sample. And I didn't look to see, but I think this is the one where he alluded to that they're actually doing overruns on his buffer or something to create some of these circles. But I haven't gone into the code for this is quite lengthy, and I have not gone through it line by line. It looks kind of interesting. But basically, yeah, we've got a higher res. Oh, I like how he says, we've got to use a range of shortcuts and special case tricks to produce these images. Not very different from the hacks and workarounds that were necessary in the early days. That's true. Yeah, again, lots of hacks and stuff that we used to use way back when. Oh, one thing he said back here. Oh, no, I already covered that. I'm right. I wrote my notes in my book, so I'm going back. So now, again, for each tile, the way it's going to work is we have this image, and we're going to, again, do grids. This is 256 by 256, so we're actually going to bring this down to 64 by 64. We're going to have a grid of 4 by 4, 16 pixels. And this is actually a purely black and white image. And so what we're going to do is one grid at a time, we're going to see what shade of gray that image actually should be to help accurately represent it. And so this is kind of fun because we're going to rely on some things that we've learned previously in the book. And so we have black and white subpixels, whether they're flipped or unflipped. So if they're flipped, that's going to be a white pixel. If they're not flipped, that's going to be a black. I think I have that in the correct order. And so we're going to end up representing that pixel in the 64 by 64 as an intensity. So basically a shade of gray. We're going to take a whole bunch of, we're going to take 16 black and white pixels, and then we're going to make a shade of gray at the end. And he says, handle these problems the exact same as the quantum sum estimation problem. So we're going to use our same flip subroutines. And then we're going to use the QFT to basically sample these 16 outcomes, black or white, and we're going to try and estimate with the QFT how many of them were white. And so again, we're using that frequency estimation and other things, right? We've got a sample of data. We're using the QFT to tease out some aggregate data from that sample. And so one thing he notes here is we're having to run this several times on each grid. So if you go back to our quantum sum estimation in our QFTs, he kind of mentioned you may have to run this multiple times to narrow in on a higher confidence of what the results you're getting. And he says, no, that we'd have to do that with a conventional computer as well. So let's see. He's going to show us examples here. So here's the full resolution image. Here's what the standard conventional computer gives us. Ideal reference, again, this is if it was absolutely perfect. And here's the quantum super sampling results. Question I have often that pops in my head is, okay, where did you get this ideal reference from? If this is the best, random computer simulation, and this is a pretty decent quantum simulation, how did you get the middle one? So I don't know if this is a Photoshop routine. All things being equal, we've got lots of power and horsepower. This is what we get. And we're going to use that as our.
What I kind of assumed with this, which may be correct or incorrect, is that was a true average. So if you take the 16 pixels that are broken down for that one pixel you're generating, if you were to completely average all of them, then you would end up with that, as opposed to taking a sample, you're actually averaging all of them.
That's true. Yeah, that makes sense. And later on, he does say the more samples you take, the more closely you converge. So if you literally took all 16 pixels, 100% of the samples, then that would be this idea. So that makes sense. One thing he notes is that our pixel error is 30% smaller on our QSS results. And the error-free pixels, remember, these are the pixels that are absolutely accurate. Less than a quarter of them in the standard computing, and yet we have almost half with the QSS side.
Yeah, and this kind of bothers me because as a human, the Monte Carlo result looks closer. So if you were to ask me which of these images is closer to the original, I would pick the Monte Carlo one. Again, not having the precision of how many of these pixels are dead on,
Yeah, and I think that's where, when we get into AI and some of these other things, it really depends on how you train your algorithm. Because if you said, I want, the goal is to have the largest number of perfect pixels. Well, sure, you may have a whole bunch of completely black pixels when they should be white, but on a whole, we actually got better error. And so it's like we may have to fine tune our set of rules here to make them more palatable for us humans.
So it's interesting also that he's only looking at pixels as their 1 or 0-ness, meaning black-white, which is a little more like newsprint and not grayscale, and he's putting it on a gray background. And I think that's why, we don't quite see the effect of which pixels are computed correctly and incorrectly, because we blend them in our mind with gray.
Well, I think the original is black and white, but the output is grayscale. Is that correct, from what you got, Matt?
Yeah, so if you take a grid of these, a 4x4 grid of these black and white pixels, they'll end up with one gray pixel. If the grid happened to be all black, it would be a black pixel. If it happened to be all white, it would be a white pixel. But if there was a smattering of black and white, then you would end up with some sort of gray. And it's almost like the Monte Carlo one does a little smoother job. I don't know what the correct terminology is, but like I said, you know, the human eye almost makes that out a little nicer. Whereas the QSS result, it's almost perfectly fine with taking a stab right in the middle. Now that may be more accurate, you know, as far as having less error-prone pixels, but yeah, it definitely seems to not be as nice. So again, I did not have the ability to kind of go through each of these lines and understand what on a line by line basis. It was more just an overview. So if any of you have a more understanding of this or comments on this, definitely jump out.
Well, the thing I wonder, and maybe I'm just showing, I should have read the chapter right before the meeting, but does it say how many times the Monte Carlo was run and how many times the quantum was run? One of the things I found in my sort of research, a baseline for quantum is usually 1,000 times, which to me was a new thing. Like when I do machine learning, I don't, as a baseline, run it 1,000 times. I might run it 10 times, like a Monte Carlo. But that to me seems actually kind of like an important detail. And I wonder, does he cover that?
And a couple pages further on, it does.
Yeah. So great transition. So he talks about some of this. Our QSS shader never actually outputs a single subpixel value. Instead, it uses superposition of possible values to estimate the sum you would have gotten from calculating them all up. So this is interesting. The Monte Carlo method, if I understand it right, if you're only grabbing one pixel, let's say one iteration or something, you're randomly picking a pixel and you're saying that is the pixel I'm going to show. You're not sampling a whole bunch of pixels and coming up with an average like that middle reference picture. Whereas with QSS, you literally are saying, let me do an amplitude amplification across all 16 pixels, and then let me do a QFT to get the sum, or what we think the sum would be, for that whole grid. You literally are sampling all 16 at the same time. So that's interesting. And we're only grabbing the sum because we're not reading every single one, right? We're using the QFT to pick out the ones that we may want to care about. And he says, if you actually need to calculate every subpixel value along the way, then conventional computing approach is a much better tool. So this again gets into where does QPU fit, where does traditional. If you're grabbing a large amount of data and you're trying to tease out the interesting parts, you know, QPU and QFTs and stuff sound like a great way to do that. But if you really do need every single bit of data, then maybe traditional computing still offers the better option. So yeah, he starts talking about the fundamental difference between the two. Let's get into that. Conventional super sampling, as the number of samples increases, the result converges towards the exact answer. So like you were mentioning, Jeremy, earlier, I think that reference image, they did literally sample all 16 subpixels and came out with a perfect average. As the number of samples increases, the probability of getting the exact answer increases. And so now we're back to, okay, well, with everything in superposition, I can get closer to the exact answer. Now, running 1,000 iterations, 60% of the time I can make it the perfect answer. 10% of the time I may get another slightly off answer. 12% I can make another one, you know, but our large number of samples, the closer to the probability of getting the right answer. So I think that may be interesting in some of those other images where a lot of those pixels are dead on. There's a lot that aren't. And so I think that may show us why we're getting the look we're getting. So now he gets into how QSS actually works, the actual sampling. So we're combining the amplitude amplification iterations with the QFT, allows us to estimate the number of items flipped by whatever logic we use in the flip subroutine of each AA iteration. So remember, in this case, the flip is actually the drawing program. The code we used in the very beginning to create that image is our flip code. So, and we're either making pixels black or white. Black, they're not flipped. White, we flip their phase to 180. So that's what creates our image. And then now we're using the way AA and QFT work together to help us count the flipped items. So first we perform the AA iteration. And we're using our number of counter qubits in here. Let's see. So yeah, if we now use head operations to prepare our counter register in superposition. So we've taken our information we're looking for, we're throwing it in those counter registers, and that's where we're doing the QFT. I'm sorry, I got lost here. We'll be performing a superposition of the different number of AA iterations. So the read probabilities for multiple flip values in the register are dependent on the number of AA iterations that we perform. We noted earlier, this creates those oscillations like those mirroring effects. Now this is where, again, it got a little muddy for me. I'm trying to remember everything I've read so far in the first 10 chapters of the book. But because of this, when we perform a superposition of different numbers of AA iterations, we introduce a periodic oscillation across the amplitudes of our register. So again, when it comes to reading the frequencies in coding registers, we know the QFT is the way to go. I don't know that he actually addressed, are we accommodating for this mirroring effect?
What I think that he's doing is he's, having a lot of assumed knowledge here. Again, as soon as I hear this, then in my mind, I'm drawing the little XY grid with the, amplification and remembering the symmetry and all this, but I've read the book 3 times.
I remember that, and I remember in those sections, he almost said, if you are in a situation where you're getting mirrored, you almost need to just throw out that other half of the results, right?
Yeah.
But I don't know that he's somehow throwing out the results, or is he implying this is where some of our error is coming from?
Again, as you go through it, he's going to show you why the error is so pronounced because of this, if I remember correctly. So just keep going. Okay.
So what he does is when we're reading the frequencies and code registers, we know the QFT is the way to go. He's going to determine the number of flip values. So this is the key. We're actually looking at the number of flip values, which is our number of white pixels in that grid, right? Knowing the number of subpixels we've sampled. So again, knowing the size of our grid, which in this case was 4x4 by default. We can then use the term the brightness. So again, we're going back to, we're taking a black and white image. We're taking a grid of 4x4, so 16 pixels, and we're coming up with a gray value. So that's our brightness. And we're using the QFT to count in one fell swoop how many white pixels or how many flipped pixels are in our grid. So this is kind of interesting. Rather than, a normal computer, you would use Monte Carlo, grab one, maybe a few more pixels, and then average those together. If you really wanted to be ideal, you would literally average all 16 through some loop. You're having to do some sort of looping and aggregating. But here we're going to use a QFT and we're going to do it all in one swoop because, we're using superposition, and that's just the coolness of quantum computing. And he does say it's a little harder to graph this than all his text. So Lynn, this is where he gets into his multiple samples. He doesn't actually say how many samples he took in that previous one. For me, just kind of eyeballing it, it almost looked like he was around the 7 iterations. So maybe 15. So again, he talks about the more counter qubits we use, the better sampling at the cost of having to run our code more times to create off this sampleable. And so he hasn't addressed yet, okay, we get our result from our QFT. And remember, the QFT is not a raw number. It's not like if you have 7 white pixels, it's not returning you a 7. it's going to return you some sort of frequency or number, and I don't remember the exact calculation for that. And so he basically says, now we need a lookup table. And so he talks about the lookup table that he has here, because these are obviously not the circle diagrams anymore. We're not dealing with our pink and green circles. And Nuri, you brought up a good point. If you look, he actually generates the graphs, which are pretty cool, generates the images. Mm-hmm. And so how do you translate the number you get from your QFT operation into a gray or a white or a black? And so he talks about this, and we actually have a lookup table. Now, again, how he generated his lookup table, he has the code for that later on, but I didn't quite understand the math or logic behind why it comes out this way. But one way he says is to, the lookup table is specific only to how many counter qubits you're using and how many samples you're taking. And so it actually has nothing to do with image. This is what it will look like for a 4x4 tile size and 4 qubits in your counter register. And so the way he says to read this is you've got your result of what you get from TFT on the vertical axis, and then your, again, I don't know if this is really the confidence, or let's see, it says, yeah, the x-axis, and numerous possible outcomes we might read. The y-axis, I'm sorry, I flipped that. The y-axis is the number of possible outcomes we might read. The x-axis is the different possible numbers of subpixels within that tile that could lead to these values. So the different possible values that could lead to that read, and there's that could probabilistic phrase again, right? So he goes on to say, let's say we got a result of 10. So we're pretty confident that there were 5 white pixels, but there's also a good decent amount of chance that could have been 6 or 4. If we got a read of 1, we would be 100% confident that there were no white pixels, right? If we got a read of 0, we would be 100% confident that there were 16 white pixels. And so that's how this lookup table works. If we got an 11 out of our, if we got 11 out of our QFT, pretty decent chance there was 11, but there could be 10 or it could be 12. What's really interesting is if you get a 15, we're mildly confident there were 15 white pixels, but again, there's not much other chance. I don't know if the chance is so low, so I should read this as most likely you've got 15 white pixels, or if the idea is, you know what, there's a decent chance you could have 15 white pixels, but it could have been anything else. But that's how you read this table. So again, this example is kind of interesting, and there's so many steps to it, but generating this, the quantum portion of this code is actually very small. I think there's a lot of other parts of the code that would be handled by a normal conventional computer, and then you would hand off the sampling to your quantum. And then maybe when you get those QFT results back, you would run through that lookup table on a conventional computer. I'm not sure that. I keep trying to look for the dividing line. When would I hand this off to a quantum machine in the cloud and then get it back? And Lynn, as you mentioned, running actual quantum hardware can be extremely expensive. So I'm assuming, at least in these early days, we would try and slice and dice our code down to where we're only sending the actual quantum required parts of our program off. So that's where so the lookup table is used by the algorithm to determine the final result. How do we get our hands on a lookup table? Well, then he's got code for that as well. And so you can actually adjust your code depending on how many, what your grid size was and your number of counter bits. Did you guys want to go through that at all, or the code? Again, I'm not relying on the code a whole lot.
Well, one of the things that, that is now introduced in the book that you'll see next week, because I think you had the same challenges that I did. I just had more time. When you have code like this, that is mixed, quantum and classical, I find that to be really, really difficult. I'd rather have two separate methods, basically, because I really need to understand what part's quantum and what part's classical, and just kind of going back and forth and having to parse each line is really, really hard for me. Because again, as a cloud architect, like you said, when would you use a QPU? Like when would you use a GPU? Because you got to pay for it, right? So I want that very well encapsulated so that I can understand this is the section of this routine. Like I would and I did for next week. I would refactor it to this is the quantum part, this is the classical part. Do you know what I mean?
So I'd like to understand that more, Lynn, because the way my mental model worked on this is that the iterative JavaScript was code creating circuits.
Yeah.
The circuits themselves are on real hardware would be represented as hardware, go work on that. Here's the daughter card, go work on that part.
Yeah.
So how would you separate it? Like this doesn't actually run anything. This sets up the circuitry to be able to run.
Well,
this
yeah.
kind of like a code generator in my mental model.
Yeah, yes and no.
Yeah.
I mean, one of the other things that I've discovered, which was so interesting to me, is local run versus local simulator versus cloud simulator. And one of the things that I saw in the IBM examples and the Qiskit examples is they actually count the number of operations. This is some stuff that you had talked about in earlier weeks, Nuri, in terms of performance. And there was one example, it was actually a Q# example, where the woman who demonstrated it showed that it actually couldn't be run on the cloud simulator because it had too many iterations of the loop. The circuit was too big, basically. And so she had to refactor the code to make it the quantum portion of the routine simpler so that it was cost effective to run it on the cloud. So it's maybe like a bigger focus, but it's something that I start to see in this chapter and we'll really see in the next chapter, because Shor's algorithm is one part is classical, one part is quantum. It's like very, very, that's the standard pattern. So I don't know, Matt, did you feel that at all? Or is that just my sort of challenge with this?
No, I definitely felt it. And Nuri brought up a good point too. I guess I was thinking, I'm not a cloud architect. I know a little enough to get dangerous, but I'm thinking, okay, if I were to have a routine, I've got some sort of workflow where I need to pass a portion of it off to some quantum computer, I would almost have, queues and event streams. But when I got to that bit of code, okay, I'm going to throw that onto a quantum queue, and then some quantum computer is going to pick that up, do the work, and then it's going to throw the result back onto a traditional queue where I might take that and do that.
Yeah.
Now, to me, that's assuming there is a quantum only pipeline somewhere there. Nuri, you brought the idea of a daughter card. So I don't know, would we throw a larger portion of the program at the quantum computer or the Amazon hardware bracket or something else? And would it be smart enough to say, I'm going to run the majority of this code on my traditional hardware, but I'm going to throw off the quantum stuff? I don't know.
I can tell you the answer to that. It's not yet.
Yeah.
So there aren't, and that's an area of active research. So if you're going to actually run something, then it's like the old days of any type of computing, but where you have to understand how in Nuri's example, how big the circuit would be and whether that can effectively run. There's not like a optimizer per se.
Yeah, and that's where my mental model for understanding this was that the programs we see in pseudo JavaScript-ish are preparing the punch cards that contain both the instruction and the data loaded into the instruction, with the exception of the haddiness of the instruction that would generate its own state or its own quantum state. So we feed it any and all concrete to the inputs, and we compute a circuit to solve the problem with this. So a lousy example would be that if I had streaming data coming in and I needed to do some crunchy crunch on it, the values, the numbers that came may result in creating new circuit just for that number because it happens to be one way.
Mhm.
And therefore, the notion of this division between the imperative code that generates it versus the actual quantum is synthetic at this point, because it's like what were they called, the computers that you can program on the fly, the electronics, programmable gates, so there's this class of electronics, and instead of like implementing the silicon and saying this is the logic, you can programmable gate array, PGAs. So it's kind of the equivalent of PGAs, where you program it and tell it to run kind of at once as a package.
Well, I know FPGAs.
Right.
Is that an instance of
Yeah.
that? So like
Yeah,
that?
well, no,
Yeah.
I don't know. I'm saying,
Yeah.
in my understanding of what we're doing here with programming quantum, we're actually more akin to FPGAs, where we're saying we're creating a whole new circuit on the fly for you to run. And a second from now, we might reprogram you altogether for you to run again. So when
Again,
we
I'm no-
actually
I-
want the
I-
result,
I'm-
we
yeah.
trigger the execution, but we're actually handing over the whole program, the re-architecture of the FPGA to produce the result, then run it, and then wipe it and ignore it and do it again.
Yeah, I believe you're correct. I have exactly had one client using FPGAs based on my data point of 1. That sounds right. But poor Matt, we're really derailing you. I'll be quiet and let you proceed.
Oh, no, that's fine. And I'm totally losing it, but when Google kind of flipped some of the cloud stuff on its head, I don't remember what it was called, but they had a white paper, and they basically, we can, a lot of our big, highly intense code can be refactored down into your reduce and map. That's what reduce and map concept, where you can chunk over terabytes and terabytes of data using very small amounts of code and reduce this over a scale place. And so I'm almost, but you didn't write general code and throw it at their cloud. You had to come up with your map and reduce functions. And then you fed the code into that, and it ran the functions on the code until it processed it all. So I'm almost wondering if we would come up eventually with our QPU functions or algorithms, and then we would feed the code in, let it churn on that, and it would spit that out again on some sort of
Well, to this particular example, I would say, what I thought of when I was reading the chapter was, like Nuri was saying, medical imaging. Trying to do identification of disease state, cancer tumors, that kind of stuff, where you have lots of data that you need to analyze. If you have very sick patients, lots of representations, and it's the needle in the haystack, right? You need to analyze lots of data and quickly find where the disease area is. To me, that would be a QPU job. And then you would go to something that is going to be more specific, which they showed the Monte Carlo or whatever, to be able to find what is, okay, this looks like could be tumor, this looks okay. Now let's go, once we see these areas, let's then get precision in the areas.
yeah.
So rapid medical imaging, to me, would be an obvious sort of use of this.
Yeah, I love it. So he talks about building this. He talks about what different QSS tables look like, and he actually has code where you can generate this. And he does mention the larger your tables get, the more intensive the code gets. One thing I will say is, in his code, when you run it, he's got a nice little warning that says, this could take a long time, but click here for a video. And it actually goes to a video I think he gave at SIGGRAPH, which is it's a global conference for, used to be graphics. I'm sure it's much more than that now. I've only started watching a little bit, but it looked interesting, so I'm going to go back and watch it. So anyone who's watching the video here, definitely go check that out. And then he talks about confidence maps. And so with any of these lookup tables, we mentioned, okay, if I get a value, I'm going to see what row I'm in, and then I'm going to go see what column I'm in, that shows what possibly, what are the probable white pixels. Well, then the next question comes up with, well, back on my other confidence, lookup table here. Again, if I got a 1, I'm 100% confident there were no white pixels. If I got a 0, I'm 100% confident there were all white pixels. Some of these I have a horrible probability. So, okay, when you design this picture, what really is your confidence as to whether what you're getting is accurate? And so then he talks about coming up with a confidence map. And he actually comes up with a graphical representation as to where it's confident. I didn't see that he stated it specifically, but I believe the white values are where it's nearly 100% confident that I got the right answer. And the gray values are, it's not so much. Did you guys get that?
That's how I interpreted it as well.
Okay. So looking at his confidence diagram, I'm much less impressed because I see a lot of gray. But again, I don't know, maybe black would be, I have very little confidence. White, I'm 100% confident. So if you're gray, I'm pretty well, at least 50% there. And maybe it's just visually not appealing, but again, they said they had like a 41% error-free rate. So while you may not be totally confident in our very deterministic world, if we run this 1,000 times, our chance of getting to the right answer is much higher. So maybe our confidence on the just one iteration or something isn't all that great, but we run this 1,000 times, we're going to get much closer to a nice error-free result. The last section here, adding color, he basically says, okay, we've been playing with 1-bit monochrome black and white graphics. How would we do this with other colors? And he does say, if you were to try and do this with more colors, we would lose some of the basic primitives that we've been using so far. Now, I think that's because the amplitude application or some of the things, we're used to either using a phase flip, it's either 0 or 180 degrees. Anything in between we start to lose. I don't know. He doesn't talk about how you represent images like color data, 8-bit or otherwise, in a QPU register. But he does talk about that there's ways to do that. I think it's towards the end of the book. There's chapters that talk about the reference, other ideas. So I don't know. In the circle diagram, we're only seeing the amplitude, but Lynn, as you mentioned, like on the IBM side, we've got the sphere. I would be surprised if you wanted to store a 3-color value RGB on the different axes of the sphere or something. Maybe you could do something with that. But anyway, so he says, okay, well, again, this is more just a fun throwaway on the side. We can actually use some older fun hacks where we could do a sampling for just the red values, sampling for the green values, and the sampling for the blue values. And then we can average them together. And so he notes that the way we do it right now, this would only allow us 8 colors. This is what it would look like. So if we were to sample an image just for the red values, if we were to sample images for the green values, sample images for the blue values, and average them together, again, it looks like our old school, computer graphics way back in the day. And that's how they did a lot of it back then. So that's kind of fun. Where I got lost is he said, this only allows us 8 colors, including black and white. However, super sampling allows us to blend subpixels together, effectively producing a 12-bit pixel image. So I'm still working out the math as to how he got to 12-bit. 8 colors, I got it pretty easily. And then we're pretty much at the end. So it says it's worth noting quantum supersampling to produce novel noise distributions potentially has relevance beyond computer graphics. So if you look at the Wikipedia article, it starts talking about pixel shaders, and it mentions there's a lot of pixel shading functions and methods that are used for things that have nothing to do with actually shading or changing the outcome of a pixel. And there's actually methods for pixel shaders, even though they're not pixel shaders, that have nothing to do with graphics altogether. So the fact that that's where it came from, the idea that it's used other places. So I kind of like that idea, because that initial graphic to us may not look all great. Case again, medical imaging, maybe that's a great one. Okay, if we see this gradation or haziness or this kind of granular noise, it's hard for a human to pick that out. But all of a sudden the computer says, wait a minute, there's a big white pixel over here. That's something you may want to look at. Maybe that's, however that might be used as something that can be done beyond what we would normally see. So that's pretty much the end. Sorry, kind of flying by the seat of my pants there.
Well, it's convenient because we're at the end of the hour. So thank you so much. I really, really learned a lot as usual. And I really appreciate it. So I'm going to stop the recording here.